So welcome everybody to our presentation today about the ammonia economy. Speaking to you this afternoon from our backyard, but such is the way of science in the time of COVID. Become quite a common experience, I think. Many of you will have heard at some stage of the hydrogen economy. That's a concept that's been around for generation. The idea that our energy source and fuel of the future could be entirely built around hydrogen as the material that carries the energy from some renewable source. And that concept has re-emerged very strongly in the last few years to very much becoming a reality today. But during that development over the last few years, ammonia has emerged both as part of the concept of the hydrogen economy, in particular as the energy carrier within that concept. And then really recently, within the last year or two at the most, many have begun to realize that ammonia itself could be the ultimate future of energy, shall we say, with hydrogen very much just a minor part of that bigger picture of ammonia. So we're now referring to this as the ammonia economy, with hydrogen as being a stepping stone towards that in the future. So what do I mean by the phrase, the ammonia economy? Sorry. This picture tries to summarize it all. So what you see here is a whole world of energy, all being based on and revolving around the use of ammonia as the energy carrier. So on the left, we have renewable energy generation of traditional sort, which of course goes off to immediate applications of that renewable electricity. But any energy that is excess to requirements, or it may even be that some of these installations of solar and wind are put in specifically for the following purpose, goes into this electrochemical conversion in the middle of the slide here. And this particular device can can be either producing hydrogen or ammonia. It's a very similar technology for both. And that's how one concept has evolved into the other. But in the case of the product being ammonia, then we move to the middle of this diagram, where we see all of the things that can actually be done with ammonia. The storage of ammonia in tanks of various sorts, pipelining of it, shipping of it in a global context is all very much an everyday technology. It's all present today very much around the farming industry, the fertilizer industry, and also for other chemical manufacture. So ammonia is a major product, but it's made from fossil fuels today. What else can we do with ammonia? Well, this is the realization that has emerged very strongly in the last few years. Ammonia is certainly useful in engines of all sorts, including very significantly in marine engines. Effectively, ammonia can replace diesel in any kind of diesel engine. So then we have trains and buses, cars, even planes are possible to run on ammonia. Using ammonia pipelined to buildings for direct heating or energy generation, electricity generation from ammonia. And then completing the circle around the outside of this is the nitrogen gas, which went into the process in the first place to make the ammonia from the atmosphere, is returning effectively to the atmosphere and ultimately forming a closed loop. It's very important that this be a closed loop of nitrogen being used to make the fuel and then being returned to the atmosphere as N2. Well, we'll return to that big cycle of N compounds towards the end of this presentation. The origins of thinking about ammonia like this actually predate the need for a replacement fuel, shall we say. Ammonia is, as I said today, is made currently from fossil fuels, mostly gas, but sometimes coal, in large chemical engineering plants called Haber-Bosch plants, and these exist in a relatively small number of places around the world, because these are major installations, usually based where there is ready supply of natural gas or coal. They, because of their use of fossil fuels, they currently, that one process, mostly targeted towards fertilizers, is today responsible for about 2% of global CO2 emissions. So it's already a problem, but it's equally, of course, important to recognize that it's responsible for feeding, supporting the agriculture that feeds a very significant majority fraction of the planet. So we have this uncomfortable nexus that has emerged between food security and climate security, so to speak, revolving around ammonia at a relatively significant level of emissions. This is bigger than many countries, including Australia. So it was that momentum, if you like, that started to generate the thinking process around how could renewable energy be used to make ammonia. The potential to do so at a major scale. So this is the other emerging concept, if you like, in recent times that combines with the need to replace fossil fuels, that encourages one to start to think about whether it's hydrogen or ammonia, but some renewable energy-based fuel as being a real concept in the decades to come. So this diagram shows total solar insolation at various parts of the world, averaged over the whole year, night and day, summer and winter. So you might call this an annual average. And then if you look at the numbers on the scale at the bottom here, you can see that this varies, not surprisingly, in different locations around the world. And the very dark round colors, of course, are where that is most intense. And if you observe from an Australian context, it's rather interesting to observe that if you ask where are the most intense solar insolation aspects, regions on land, obviously Australia jumps out at you as being one of the obvious places to put very large solar arrays. And the potential there is further exemplified by this little yellow square that I'm showing here. This is a little square of land, well, not so little really. It's 250 kilometers by 250 kilometers approximately. So if you can imagine that in the context of the continent of Australia. And if you were to put, as noted on the bottom of the slide, relatively standard commercial solar cells onto that area of land, and allowing for the solar insolation that's possible and the efficiency of the cells, you could generate on that land 25 petawatt hours per year of energy. That's an amount of energy being generated each year. If I was giving this seminar live, I would ask people in the audience to speculate just how much energy that actually is. And unless you're somebody deeply immersed in large-scale energy supply, it's not a number even converted into other forms of orders of magnitude. It's not an easy number to comprehend. So I rarely get somebody who's able to guess what that represents. Actually, it's the energy supply, the electrical energy supply of the whole world, just from that one little yellow spot. No, we're not actually saying that we're going to pick a spot and cover it with solar cells for 250 kilometers on a square. But to put that in context, that amount of land is only the size of the 4 largest cattle stations in Australia combined. And converting some of that land in those cattle stations and other land around and other cattle stations to a mix of cattle and solar farming is certainly a very, very valid concept, and one that the farming community that's involved in is extremely keen on. So this, from a land use point of view, this is not an outlandish idea. For Australians that might be listening to this, it's also interesting to bring this to a slightly more local context. Here's similar data from a site, from an organization that most of us trust pretty implicitly, the Bureau of Meteorology in Australia. This provides the same kind of information, different units here, and I've given you the conversions at the top here, and it just shows you the same idea of where the really intense solar insolation really is in the country, again averaged over summer and winter and night and day, and not surprisingly it's sort of the dry center and the north and the west. I've also marked there 2 or 3 interesting political hotspots of late. You notice the famous Carmichael coal mine that's been the subject of so much debate and protest recently. And you notice kind of where it is. It's in a region that is pretty high still, in the 20 to 22 megajoules per square meter region. It'd be very, very viable, much more viable than in a very large number of other places in the world to put large solar arrays. And you could even bring those solar arrays even a bit closer to Boyne Island, which is one of the very significant Queensland aluminium smelters. So aluminium smelters use large quantities of electricity. Most of it comes from coal today, at least in Australia. And to convert that to solar, of course, the problem is the intermittency. And ammonia and hydrogen as easily stored materials could easily be the answer to connecting large solar arrays in this sort of part of the country with users such as Boyne Island. That's a local use, and you can imagine that being in pipelines. But what about taking all this energy to the distant markets? We call this problem, we call this the problem of stranded energy. Lots of energy available, and I've only just mentioned solar here. There's, of course, lots of potential around wind and probably increased potential around hydro. That's why New Zealand is showing up on this graph, on this picture. But how do we get it to these distant markets where the capacity to generate renewables is not so great? In other words, what's in that boat? And what is this processing plant here that's taking this energy that we certainly could generate? And the answer has a couple of versions, and this is the concept that we've developed around this. We think of this developing over a number of generations. This exportable material that we call liquid sunshine or liquid sunshine as a fuel, can be, first of all, converted into hydrogen, which we refer to as green hydrogen because it's made from renewables, and to export it, it has to be liquefied. So that's kind of that. I'll come back to that problem, but that is not a straightforward or costless technology. But that's happening, right? And that's the hydrogen economy that we've heard about so much. If you have green hydrogen, then in generation 2, you can see the potential for using that green hydrogen in the Haber-Bosch process. First of all, to make the ammonia for fertilizers that we desperately need to turn green, but in the bigger picture, through expanded Haber-Bosch capacity, then that could be the exported fuel. So ammonia is already exported in large quantities around the world on ships and pipelines, and therefore it could become the carrier of this energy. And in generation 3, it might be that we avoid the Haber-Bosch altogether, and as I will explain in this seminar, produce the ammonia by direct nitrogen reduction. In the same way as we generate hydrogen, we go direct to ammonia, and we call that Gen 3. But I should explain some of this color scheme for those of you who've come across some of these terms. Green hydrogen and green ammonia is fairly obvious. We're referring to making it from renewables. In this scheme, we tend to then talk about black or brown based fuels, so that's current day fuels, including current day ammonia for fertilizers, as black or brown, right? Because they're referring to the fossil fuel origins. There's an intermediate color that's often referred to, and it's important to understand what this one means. We talk about blue hydrogen or blue ammonia. That's black hydrogen or ammonia, but with carbon capture and storage implicit in the concept. so the carbon isn't let go. So it greens the process somewhat, but there's still this issue around carbon capture and storage that is implicit there. And for anybody who's wants to sort of see the complete picture, there's also some discussion around what's been called purple hydrogen and purple ammonia, which refers to that being made from nuclear electricity. Okay, let's talk about hydrogen for a moment. So this is sort of a pit stop on the way to the full-blown ammonia economy. In this picture on the right, I'm showing you what is a very, very basic laboratory experiment to make hydrogen from water. Salty water will electrolyze, producing hydrogen at one electrode and oxygen at the other electrode, which we're collecting in those test tubes. You can see the tiny bubbles streaming off one of the electrodes there. And hydrogen is readily used in fuel cells, in cars. It can be burnt, so it forms a good flame, and so on. So hydrogen implicitly is a good fuel, and it's relatively easy to make from renewable electricity. The question is how to move it around. So bulk carriers for liquid hydrogen, it's too voluminous to move around as a gas. We have to liquefy it first, which means cooling it down tremendously below room temperature. So a lot of energy required in that cryogenic liquefaction process to place it on ships like this, and then to move it from places like Australia to the markets of Asia and Europe and North America. However, as I say, that is an energy-consuming process to liquefy it, and the safety aspects of moving larger quantities of liquefied hydrogen around still not resolved, and that so at very large scale, moving hydrogen around is a technology that is fully to be thought through and developed before this can really become our true hydrogen economy. So while that's been going on then, we've begun to wonder, well, what else can we do with the hydrogen in order to make it easy to move around? And this takes us to Gen 2. So we're still on the left of this diagram talking about making hydrogen, but rather than shipping it directly, the Gen 2 concept puts it through the Haber-Bosch plant. So this little blue box is actually a very large billion-dollar piece of chemical engineering kit, which takes in nitrogen from the atmosphere. It takes in hydrogen from this electrolysis process. It makes ammonia. This is all now standard technology. The only new bit is here. And ammonia is relatively easy to store in things like this small container I'm showing here, and liquefy. It's liquid at only 12 bars pressure, which is very mild at room temperature, or at about -30 at 1 bar pressure. At which point it produces a relatively energy-dense fuel, which is why it's even possible to consider flying a plane on ammonia. And once you've got that, as we've said, you can move that around, and then the applications of that are effectively two branches to that. In the hydrogen economy picture, this is only a device for moving it around at port or a point of use, such as a fill station in the middle of Tokyo. The ammonia can be cracked back into the original nitrogen to release the hydrogen, which is then used in a fuel cell. And there are fuel cell vehicles that are now readily available from companies such as Toyota and Honda. On the other hand, it is actually well-known technology that you can run engines from as small as car engines to as big as marine diesels on ammonia. So ammonia engines are a ready application, which means that this cracking part of it isn't actually necessary. So we are beginning to see the possibility of a fuel technology based on ammonia when we recognize this. And then when we then step this picture to Gen 3, where I've changed what's going on in this cell, and have been able therefore to generate ammonia directly, everything else is the same. And what I've managed to skip is the Haber-Bosch process, which is a major cost element in the previous picture. So it does seem like this is an important vision for the future that our electrolysis equipment here is directly producing the ammonia, not hydrogen. And then we can go directly to these applications that use ammonia. So how do we make Gen 3 ammonia directly from nitrogen? So the electrochemical process that we're talking about there is apparently rather straightforward. We just need to take nitrogen, some protons, some electrons. This is our renewable energy to make ammonia, and the potential at which this in principle can be carried out at is actually easier, if you like. It's above, so therefore it's somewhat easier to do so in energy terms than making the hydrogen, which was kind of where this discussion started. So this looks promising. The two aren't so very far apart, so if we're not careful, we're going to end up making a mixture of ammonia and hydrogen under conditions where both are present. You notice the protons that are present in both of these reactions. So the question becomes, can we suppress the hydrogen evolution reaction to achieve high cell activity towards ammonia? And that problem is significantly worsened, if you like, because by the fact that nitrogen, which is the reactant in the top reaction there, is very much not very soluble in most solvents, especially water. And there's the problem. So it's very easy to reduce water or protons out of water. And in the case of nitrogen, we just don't have much of it to reduce. And the competition then with the hydrogen reaction becomes intense. So there's the challenge in this concept, is how to make the best of that situation. So here's an example of us beginning to do this. I won't go through all the technical details of this slide, but the point is, it is possible, we think, to carry out a reduction reaction that does produce ammonia under moderately mild conditions, but still always producing a fraction. That's what this graph over here in the bottom right is all about, producing a fraction of other things, mostly hydrogen. That's not to say that the hydrogen is useless in this, but it does create a problem of separating these two energy containing products from one another to apply them to their separate uses, so to speak. So that's where the field is very much at, trying to do this and trying to make this practical. We get a lot of support in doing this sort of thing from our theoreticians who are able to model what's going on here. And this is a particular catalyst that has emerged from our group over the last couple of years, where we take a molybdenum sulfide material. So the modelers can visualize it as this. This is the surface of the electrode, on which are placed little tiny clusters of ruthenium atoms. So 117 of them in this model. That's rather precise. We can't do that quite that precise in the laboratory, but that's approximately the idea. And then the combination of the two materials, especially sort of at the edges between the two, support this reaction. And if you were to follow all the individual steps here, which the theoreticians can calculate their way through, you see how many steps that there are, in fact, in such a process. This is why it's, in fact, quite a difficult one to get right. But this helps us understand what would be going on a material like this, with ammonia being released in a first and then a second release step. Each nitrogen produces two of these. So this is the modern way to develop and understand catalysts like this. And with materials like that in mind, our hope is that we'll be able to scale some of these concepts up, and here's some devices that go beyond the simplest small electrochemical laboratory cells to something that is the size of a hockey puck, as one visitor described this thing as, and then into something that is beginning to look more like a small fuel cell. This is about the size in my hand there of about a size of an iPhone, and inside we have these plates that are what would carry the catalyst. That's where we see this headed, and that's about the scale of it in our near future. But before we finish, it's important to step right back from the laboratory to the very big picture here. In this concept of the ammonia economy, we're visualizing a vastly increased use of ammonia not just for fertilizers, but as a fuel and as an energy carrier to generate electricity in distant markets from the distant from the place where the renewable energy is actually generated. So our whole energy market, if you like, begins to revolve around ammonia. And of course, as I said at the beginning, the nitrogen that's produced by the use of those fuels, back to the N2 molecule, must then effectively become part of the global nitrogen cycle in a harmless way. So what do we know about the global nitrogen cycle? And that's what this slide is all about. I won't go into all the details here. I'm not sure that I'm even capable of. This is not our area of expertise, and I strongly encouraging anybody who's interested in this to look deeply into this collection of papers in this philosophical transaction issue that was very much about the whole N cycle, the global N cycle. In order to understand it a bit better. But as we looked at it in overview, and we've reconstructed this diagram from a number of diagrams in that issue, we were able to make a number of observations. So first thing we tried to do was understand the fluxes here. So what's called fixed nitrogen, which is all the nitrogen-based compounds that are being made from the atmospheric N2. So all of those sort of being fixed and then ultimately being released back by various mechanisms, including various biological mechanisms, including biological nitrogen fixation, BNF. So this is plants fixing nitrogen. It's very important that they do. You see them as happening both on land and in natural forests and so on, also in the ocean. And we also see various enzymatic type cycles in the ocean and on land that ultimately release compounds, including ammonia, but most importantly, nitrogen back into the atmosphere. And these numbers are in teragrams, which is millions of tons per year. So what do we observe if we try to add all this up? So what we see is that the total downward arrows, total conversion from the atmosphere to various forms of reduced or reactive nitrogen, anything other than N2 in other words, is about 413 teragrams per year, all the downward arrows, and about 50% of that is due to us. 50% is anthropogenic. And what is that? That's these processes. This is the Haber-Bosch process to make fertilizers. It's agriculture, and the biological nitrogen fixation that supports, and its energy generation. All of these things create reactive nitrogen materials, which is possibly fine. It's important to note this 50% fraction. The total return to nitrogen or deposited in land or ocean in this only seems to add up to somewhere in the region of 250 to 350 teragrams per year. So what are you, if you're adopting a bookkeeping approach to this, you immediately have to say, well, actually, we don't really know enough about this, and then the books don't seem to balance. That's an uncomfortable observation to make, because what we don't want to do, clearly in this endeavor, is make the same mistakes with nitrogen and ammonia as we, humankind, have made with carbon and CO2. For 200 years. We don't want to make those mistakes all over again with nitrogen. So balancing these books and understanding these global cycles is a rather important matter here. Let's keep going with some of our observations. It's important to recognize that our use of some of these agricultural nitrogen compounds is actually rather inefficient. By the time they get to us, only about 17% of all of that is actually consumed by us. The rest is either lost or is in inefficiencies in that overall process. Where does it all end up? One way or another, a very large amount of it ends up in the oceans. So either through us or runoffs from fields or acid rain from the atmosphere. One way or another, a lot of this ends up in the ocean, in the water courses and the ocean. And if you look at the the overall load then of nitrogen that is being processed within ocean cycles, it's approximately double what it would have been in the absence of these human-based processes here. So we're already, with what we're doing, approximately doubling the load on those processes in the ocean. Is that a comfortable situation? Well, we need to notice that N2O, N2O is a very seriously damaging greenhouse gas, has a lifetime of over hundreds of years in the ocean. The nitrates, which are the ultimately oxidized form of many of these compounds, so that's where they end up before they get denitrified by enzymes and organisms, could have the effect of fertilizing oceans in selected regions. And accumulation in deep oceans is quite a significant fraction of material in a way that is not entirely understood, and where it goes and how long it will stay there is not well understood. So remembering that we've only been doing all of this for about 100 years, that's the 100 years since the Haber-Bosch process, one does end up with the feeling that there's a lot here that we don't really understand well enough on the time scale that is long enough. So N2O lifetime of hundreds of years in the ocean, and this is a very damaging gas in the atmosphere. Bottom line, my message here is, I think as we approach the ammonia economy, we need to understand these processes in much more detail, and I think research needs to be directed towards this kind of research. It's as important as developing the catalysis side of things that we're working on, in order that we, as I said before, don't make the same mistakes again as we did with carbon. So let's maybe leave that there and draw this to a close. Just to summarize, that pathways towards our ammonia economy as a potential overriding energy economy for the planet, so to speak, is becoming cleaner, with a stepping stone that involves hydrogen, both as a fuel itself, but also as ammonia as a carrier for hydrogen, but ultimately in the direct production of ammonia through a process we call the nitrogen reduction reaction. And just noticing there that there's lots of false positive reports that are coming out in that particular field at the moment. But in all of that, it's very important that we pay attention to the whole cycle. Otherwise, we're in danger of making serious mistakes again in this new ammonia economy. So I'll finish with a few thanks to our funding agencies and the team at Monash that are working on these things, and have been an important part of everything that I've talked about here today.